Greetings, my name is Ben Prater and I'm here today to talk to you about the planar numbers and hopefully convince you that unlike what other names for these numbers might imply, they are not particularly complicated nor are they fictitious. So before talking about planar numbers, we should probably review the number line. So with the number line, we have a line of numbers and we fix some origin point and we view the numbers as distances. So each point on this line represents a distance from the origin. So I can call this point A, I can call this point here B, and I can call this point here over here, let's call that C. And so each of these represents a distance from the origin. And then the question now becomes, if this is a number, it's not just enough to have a bunch of things and say that they're numbers. To be a number, we should be able to do stuff like add and multiply in a meaningful way. So what does it mean to add and multiply lengths in the number line? So that is the first thing that we'll be looking at next. Okay, so to add two numbers, what we do is we take the length, so we have this length segment from 0 to A, and then this length from 0 to B, and then to add A and B, I just take A, and then I take this length and put it at the end over here, and that's going to give me maybe a little bit longer, and that's going to give me a new value over here that represents A plus B. Now if I have a negative number, a number going in the opposite direction, then I would first go in the A direction, A amount, and then I would go in the C direction. I move this to that point. So now I go in the C direction here. And so now that's going to give me blue plus red gives me purple. And this represents A plus C. And again, we went in the opposite direction for C because C is on the other side of 0. So to get to C, I need to go that way. So first, to get to A, I go that way. And then to get to C, I go that way. Well, A moves me this way, and then C moves me that way. And altogether, I move slightly more in the C direction than the A direction. So that is how we add numbers. Okay, so now that we have a definition for addition, it's useful to verify that these definitions have certain useful properties. So the first property is that we have a 0 where A plus 0 equals A. So for any value, if we add 0, we get right back where we started, and that's just because we first go A units, and then if we move this nothing, no sliding at all, and we go over, then we go over A, and then we don't move at all, so we end up exactly where A is. So A plus 0 equals A, and we can actually reverse that around 0 plus A. And so this means that 0 is the identity. So this addition has an identity element. Another thing that we could notice is that here I did A plus B, where I did A and then added B. I could have taken B and then added A, moved this up here, and then we would have gotten to exactly the same spot. So that shows us that A plus B equals B plus A. All right. Now, if I did A plus B plus C, I'll do that down here. We have A plus B is that length. That's going to get me to right about there. And now plus C, well, C is in the negative direction. So now that's going to take me back to here. So that's going to give me, well, now it doesn't really matter which I did first. Do I add A plus B and then add C? Or do I add B plus C and then add that onto the end of A? Either way, we actually have exactly the same diagram for whichever order that we do. And so that actually shows us that we have, it doesn't matter where we put the parentheses. I should mention that this property here is called commutativity. And this property here is called associativity. Okay. So there's one other property, and that is that for any value, I can find a negative A such that A plus negative A equals 0. And this is called the inverse of A. So it has the inverse property. So this addition that we have defined of just sticking these lengths head to tail, one after the other, gives us a relationship between these numbers, these points on the line, that has an identity. The relationship is commutative, it's associative, and in fact we can find an inverse. For any value A, we can just take this length, move it to the other side, and we would have found over here a value negative A. Similarly, B, over here we have negative B. Negative C would just go in the other direction. So right there we would have negative C. Okay. So altogether, these properties, there are a lot of structures in mathematics that have these properties, a lot of them that we don't even think of as numbers. For example, symmetries and rotations of things oftentimes will have these properties. And so it's useful in mathematics to give a name for anything that has these properties. We call it a group. So these are the properties of a group. So if you advance farther in mathematics, you'll start hearing about groups, and all it means is that we have a structure and an operation relating to the structure that has these modest set of properties that are really, if you don't have these properties, you can't really call yourself a number because you can't even add them. So the next thing we want to look at is multiplication. What does it mean to multiply numbers? And to multiply them, that actually is related to stretching and shrinking, and I do not have the ability to stretch and shrink my blackboards. So I have this tool here. It is a rubber band, and I put some marks on it here. So I've got a mark on it here. I don't know if you can see it so well. There's a mark here that I put at 0. There's a mark here at 1, and there's a mark here at A. And in order to multiply A times B, what I need to do is just hold this point here at 0 and stretch this until until the point that was at 1 is now at B, and then this point here where the point that was at A gets stretched to, once the point that it was 1 and moved to B, that is now the product. So I'm going to put a little mark there, and then I can mark it in green, and that gives me the point C. So that is how we do multiplication. And some of the properties of multiplication, well, the first thing is if I multiply by 1, I'm not stretching anything because 1's already at 1, so it doesn't move any of the points. So we have that identity property because we have 1 times A equals A. Commutativity, if we had marked a mark at B, and then we stretched 1 all the way until it went to B, then this mark at A, we can see, no, we need to stretch that to B. If we stretch this to A, then the point that was at B would have also ended up at C. So we end up with, it's hard to actually show that with the rubber band convincingly, but we do have commutivity. Where A times B equals B times A. In fact, it's even harder to show associativity. Which tells us that it doesn't matter where we put the parentheses. A times B times C. I can stretch B by A and then stretch the result of that by C, or I could stretch B by C and then stretch the result of that by A, stretch A by that result. Either way, I get to the other one. So that one's a little bit more complicated. I do hope to do a future videos where I actually go through and prove that more rigorously, especially once we get the geometric tools. So that is a future, something that would be in a future video, hopefully. Perhaps it's not quite so easy to see that if I'd have stretched this unit to A and then marked where the 1 was, and then gone backwards, it would be some point originally over here that actually would give me a 1 over A. So I can actually get an inverse that way. And then, yeah. So I could stretch it to A, mark where the 1 is, and then bring the 1 back, and then that gives me the point that we go to 1 over A. So then we do have inverses. And that is a 1 over A times A equals 1. One thing is that this does not happen for 0. So we don't have an inverse for 0 exactly, but for every other number we do. One thing that I did not mention is what happens if I have a negative number. How do I multiply by a negative number? And for that, if I try to stretch it, how do I get this negative number? How do I get 1 to that negative number? Well, to do that, I would have to flip it and then stretch it. So negative numbers flip the signs, so which is a very geometric picture of that very common notation. So we have that the non-zero elements, this tells us that the non-zero numbers are a group under multiplication. And in fact, we have a further property. If I take two numbers, if I have 3 numbers, so perhaps C could have been an arbitrary number here. If I take A and B and stretch them both and then add the results, if we picture this with the rubber band, it's going to be the same thing as if I add the results and then stretch. So the order of adding and stretching does not matter. So that tells us that if I stretch A plus B by C, that's the same thing as stretching A by C and then stretching B by C and then adding the result. This is called distributivity. All right, so these are the basic properties for addition and subtraction that we would want to be able to call them numbers at all. If we don't have these properties, we probably should refer to whatever it is we're talking about by some other name other than numbers. But once you have a multiplication and an addition that satisfies these relationships, then you actually have something that is called a field. So when a mathematician calls something a field, that means that you have an addition and multiplication that have all of these nice properties that we think of in a number. So with that review of the number line, we can look at the planar numbers and what are the planar numbers. And clearly we're going to be expecting it because the planar, we're looking at them as points on a plane. And just like with the number line, we need to have an origin that we're kind of referencing from. And then I can have another point here that I'll call A, and maybe another point over here that I can call B. All right, so to add, we need to worry about addition. And then to addition, we just draw the segments, just like we did before, where we took the line segments and put them next to each other for adding on the number line. We're going to do the same thing, except for we're going to take into account their direction. So we just adjoin the segments from 0. So for example, A, we draw the segment from A to 0 and the segment from B to 0. And then A plus B is I first go in the A direction and then go in the B direction. And so that's going to give me A plus B. But notice that if I go in the B direction and then in the A direction, I draw a parallelogram. And so that shows me that this is also going to be B plus A. So we've already shown that it's commutative. And in fact, if I had a C point, let's say that I have C over here, well then that's a segment that adjoins C. So if I take my A plus B, and then add C, that gets me to there. So that is A plus B plus C. But I could have also gone B plus C. So that gives me B plus C. And if I drew that right, then if I draw the A direction here, well, if I take this A plus this B plus C, which is purple, now if I take that purple and move that over here, we can see that that's also going to be A plus B plus A plus B plus C. So it is associative. And we actually have the inverse because I could take this A, go in the other direction, and negative A is going to be right here. So we have all of the properties of a group that we want for our addition. It has an identity element. We have inverse elements. It's commutative. They are associative. So we have all of the properties that we want for addition. So that is how we add our planar numbers. Adding is actually pretty straightforward. Multiplying is not quite as straightforward. So again, we need to have a 1. And then if we have our point 0, and we have a fixed point 1, and I have some other point A, then A doesn't just define the segment that we had for addition, but we also have this segment going to the 1 and this segment that connects 0 and 1. So we can think of A as representing this triangle. And now B, suppose I have this point B, let's make B over here. Well then B is going to represent that triangle. So now, how do we multiply these triangles? And we need to use the concept of similar triangles from geometry. A similar triangle is if I take this triangle and stretch it, I can stretch it or rotate it. As long as all these angles are the same and it's in the same orientation, I can't flip it, but I can rotate it around. Then I can take the similar triangle and then move that moves the 0, 1 to the 0a, and then that's going to make another point, and that's how I multiply. So for multiplying, multiplication, we adjoin similar triangles. So what does that look like? So to adjoin, so for A times B, I need to take A and then adjoin the triangle for B. So when I do that, this segment goes to here, and then I can see that I have this angle coming off of there. So I take that angle going roughly there, and then that's going to make this line. And then if I take this angle and put it here, that's roughly about that angle. So that's going to come across like that. And then this angle and that angle should be about the same. And so this is going to give me the product A times B. And if I did that right, then if I take this triangle, this angle here should be that angle there. And yeah. So now if I draw this line here, this triangle should be similar to that. My drawing is a little bit off, so I do plan to go through, and if this video is a success, then I will go through and actually draw these things better with a straight edge and compass, and actually go through the arguments with the straight edge and compass and show how all these constructions can be implemented by using a straight edge and compass to increase our accuracy significantly. One thing to note is that if A is actually on this number line, this is still well defined, and it just degenerates to scaling exactly on whatever line. We just scale B by whatever. So there is that degenerate case. And then 0 times anything, just like with the real numbers, collapses everything down to 0. So there are those degenerate cases that we should consider with this definition. But in those cases, it's exactly what we would expect the multiplication to be. So this here argues for commutativity. Associativity is even more complicated, but we do have associativity for these. What would the inverse of A look like? So the inverse of A would actually be, well, the angle would have to be the opposite of the angle, so it would have to be on this line down here somewhere. And then we need something that when we stretch it, so actually we need something that when it stretches undoes this length of this A. So it's actually going to be whatever this length is. If we rotate that down to the number line, and then find the inverse of that, and then bring that down, that's where it's going to be, down here. So we actually can use that process. There's actually a geometric construction that actually produces that much more accurately, and that can produce this inverses. So there's actually a geometric process that can construct this given that point, so you can actually construct inverses. So this multiplication has almost all the properties we argued. Distributivity, if I rotate and scale 2 points and then add them, I get the same thing as if I add them and then rotate and scale the result. So that is a very geometric picture of how the addition and multiplication of the planar numbers work. There is one very particular point that is worth bringing up. So if I have my point, let's draw a line here that connects 0 and 1. and 1. Okay, now there is a straightforward construction for how to draw a line perpendicular to that line. And now I can take this length here and measure out that length here to get this point here. That for historical reasons, I'm just going to call this point I. Okay, and so now the triangle that I defines is this triangle here, that since these two sides are the same is going to be a 45, 45, 90 triangle. And now we can consider, well, what is I squared? Well, to get I squared, I just need to multiply I by itself. So I need to take this triangle, and then since these lengths are the same, the similar triangle, I don't have to scale it at all. And so it's just going to make this triangle over here. And since these lengths are the same and these lengths are the same, this length must be the same as that length, which then means by definition, this point over here has to be -1. So that tells me that I squared equals -1. And at this point, it's useful to give you an exercise to maybe pause the video and consider, what would -I be? And -I, what happens if I square -I? Or what is I cubed? So these are some interesting exploratory questions that I leave as an exercise to you, the viewer. So another thing that we can do is notice that if I have some other point up here, suppose I have this point A, there's a very straightforward way to draw a perpendicular here, and then a perpendicular here. And now this is just some number that this has a length that is on this number line, and then this has a length on this number line. So I can express any point here as a sum, as a point on this number line, plus some scaled value of this I, scaled by some number on this number line. And so that gives us a very typical expression for this number system that is how it's usually presented. Usually it's presented by, okay, we take this number line. Well, our number line does not have anything that squares to -1, so we're going to create this symbol I that has this property, and then just do stuff with it magically as if this works. We can just add stuff. But by defining it as a planar numbers, then we just have this point that squares to -1 by our definition of multiplication, and then we don't have to pull I out of the air. It's much more satisfying to me that we created this I. We didn't create the I out of the air, but we actually found this point that had this property. I just want to talk a little bit about two things that this presentation naturally leads into. Well, first of all, this identification of points with these triangles suggests the idea that perhaps studying triangles and this multiplication of similar triangles and rotating them around, maybe it'd be useful to study these similar triangles. And in fact, that gives rise to the whole field of trigonometry. And in fact, viewing the complex numbers as these planar numbers is actually, in my opinion, closer to the ancient trigonometry than either modern trigonometry or the modern presentation of complex numbers. This presentation would be much more familiar to the Greeks because of the reliance on the geometric constructions that I hope to do in a future video. It's much more in line with their study of geometry and trigonometry that they would have been familiar with. And the other thing that this then leads into is all of these operations that I talked about, finding the inverses, finding these perpendiculars, drawing that perpendicular line, this ability of drawing similar triangles, and stretching and scaling points. Every operation that I described on the pictures can be described using a straight edge and compass construction. So this could lead into a discussion on ruler and compass constructions, which is kind of a lost art in mathematics today. And actually there's Japanese paper folding. So all of these things can actually be done in Japanese paper folding, which is actually able to do more mathematical things than the ruler and compass can do, as long as your ruler is not marked. If you have a marked ruler, then that all of a sudden becomes equivalent to paper folding. But that is a topic for another day. So that's two things that, you know, this concept of the planar numbers leads naturally into. I guess three if you include the origami. So in closing, I want to thank you for taking the time, for sticking around to the end and hearing what I had to say about these planar numbers. But I also want to thank 3 Blue 1 Brown for posing his challenge to aspiring math creators for the motivation to actually put together this video that I've been thinking about doing for quite a while, and finally had a deadline to motivate me to actually get it done. So here it is. So my measurement of success for this video is whether or not it gets enough views and subscribers to join the partnership program, which is on the order of a couple thousand. So if I can get there, then I'll view it as a success, and I'll continue to make more videos along this lines, starting probably with going through all of the constructions that I mentioned and actually showing how they can be done with a straight edge and compass much more accurately than what I was able to do freehand for especially the multiplications in particular of the planar numbers. And even the with the number line, you can do the multiplication on the number line much more accurately with the straight edge and compass than what I could do with the rubber band if you embed that line in a plane. So yeah, I plan to go through that in the next video. So if you want to see that, like and subscribe and recommend this, and I look forward to seeing you in the next video. Or I look forward to, yeah, I won't be seeing you, you'll be seeing me, but I look forward to communicating with you in the next video. So like and subscribe, and thank you.